let us start our today's discussion. Just 1 second. Let us start out with this discussion. Yesterday, day before yesterday, in the last class, we have discussed a solution, but you could not finish it. Let us discuss from the very beginning and finish the problem, and then go for the remaining part of our discussion. A compound cylinder. What is the example? It was a numerical example. A compound cylinder made up of copper and a compound cylinder made of copper in a tube of radius A is equal to 10 centimeter and C is equal to 20 centimeter. Hence, what we are doing here, we are discussing the composite problems of let us discuss the problem which we have discussed yesterday, and afterwards we'll go for the next topics, the spherical tubes, spherical cylinders, etc. Here, what we have a compound cylinder made of copper inner tube of radius, say A, which is equal to 10 centimeter itself, and C, which is equal to 20 centimeter itself. And it is smart fitted, where delta is equal to 0. Smart fitted means inside a steel jacket. Smart fitted means what? Nothing. You are supposed to fit one jacket inside the other with hand pressure, but there should not be any force fitting, means we don't have to apply any hydraulic pressure like this, or there should not be any relative movement between the jacket as well as the inner cylinder itself. So there is no deflection among themselves due to this type of fitting itself, but they are fitted by means of hand, and they should not move at all inside each other. So we are fitting the copper inner tube inside a steel jacket of, say, external radius is given by, say, 40 centimeter D. So what we have three dimensions. One is internal dimension 10 centimeter, and outer dimension of the copper tube is equal to 20 centimeter. And as it is snug fitted, the internal diameter of the steel tube is also 20 centimeter, and outside diameter of the steel tube is also 40 centimeter itself. Now, if the compound cylinder is subject to an internal pressure of 1500 kg per centimeter square, or 1,47,009 kPa. So, determine the constant pressure PC. We have to calculate the constant pressure, which is the contact pressure, is actually not constant pressure. The pressure between this copper tube as well as steel jacket, and the values of radius stress sigma r and yes. Now, I don't know where I have up to which portion I was audible. Well, I'm just saying that internal pressure is supposed to be 1500 kg per cm square, and we have to determine the constant pressure PC, contact pressure PC, and as well as the values of sigma r and sigma theta and the internal and external points of the internal and external points of the inner cylinder and that of the jacket itself. So we have some other things are given, like Young's modulus of the steel is given is equal to 2 into 10 to the power 6 kg per cm square. That of copper is 1 into 10 to the power 6 kg per cm square. The Poisson's ratio of steel is equal to 0.3, and that of copper is equal to 0.34 itself. Now, let us go through the solution. Since the internal strength fit there is no allowance. There is allowance delta is sigma, delta is equal to 0. The internal contact pressure, there is no initial internal contact pressure. When the compound cylinders is subject to the internal pressure P, which is there is an increase in the external radius of the compound copper cylinder under the pressure P, and the contact pressure PC will be created, which will be equal to the increase of the internal radius of the jacket under the contact pressure P. So what is clear here, as there is no, say there is, it is snug fitted, there is no sink fit tolerance, sink fit allowance. So internal pressure exists no internal pressure initially. Now, if the compound cylinder is subject to internal pressure, means we have subject having an internal pressure P. It is at the inner part of the cylinder, copper cylinder. Then what happens? The external radius of the copper cylinder under will be also under P, and contact pressure PC will be equal to the increase in internal radius, and that too of the jacket under the pressure PC itself. The external pressure of the copper cylinder will increase under P, thus makes a contact pressure P. So there is an internal pressure due to the pressure of the fluid which is flowing through the inside of the copper tube. That pressure is trying to expand the copper tube, but it cannot, thus created a contact pressure between the copper tube and the steel jacket, and this increase in external radius should be the increase in the internal radius of the jacket under the contact pressure PC. So what we get out of it, one, internal pressure, which is given, which is our flowing fluid or flowing liquid, whatever it may be, and the contact pressure created by this pressure pier between these two contact surface between copper and internal cylinder, and the increase in the radius of the inner copper tube will be the increase in the radius in the internal radius of the jacket will be equal to the increase in the internal jacket under pressure PC itself. So increase in the internal radius of the copper tube will be equal to the increase in the internal radius of the jacket of steel jacket, under the contact pressure PC. So due to the action of P, the internal radius of the copper pipe will increase, and that increase will be equal to the increase of the internal radius of the steel pipe under the action PC itself, contact pressure PC itself. So due to the action of P, means internal fluid, the internal radius of copper tube is increasing, and due to the action of the external pressure inside the jacket and copper and the steel tube, the radius of the steel tube will increase to a certain extent. So first was due to P, and second was due to PC itself. Now, the displacement U1, radial displacement of due to the action of P means, and this is plus the radial displacement due to the action of PC, the contact displacement at R is equal to C, which is outer radius of the copper C will be equal to the radial displacement. It is for copper is equal to the radial displacement of due to the action of contact pressure PC at R is equal to steel due to the steel in the steel cylinder itself. First was the copper cylinder, next was the steel cylinder, and these displacement are equal to each other. So due to pressure radial displacement and due to the it will be added to the radial displacement due to the pressure PC, and that's for the copper, and radial displacement due to the action of PC, that is for the steel, will be equal to each other itself. So first we have to calculate the individual radial displacement, then we have to add them, you have to equate them together. So what will be the radial displacement of P, which is it is the equation we have already developed. So this will be equal to 1 minus the Poisson's ratio of copper divided by Young's modulus multiplied by the internal pressure of the fluid multiplied by the internal radius of the copper tube multiplied by the outer radius of the copper tube divided by square of the internal radius of the outside radius of the copper tube minus square of the internal radius of the copper tube itself. And with this, we will be add the effect of the external pressure with the copper tube itself, 1 plus V plus Q cube, A square plus B square divided by C, and P divided by C square minus A square, where A internal radius of the copper tube, C external radius of the copper tube, P is the internal pressure, and E is the eccentricity and modulus of eccentricity of the copper tube, as per our previously discussed formulas. Next, what will be the displacement of the copper tube itself is due to the internal contact pressure PC. It will be a same, these two things will be same, but here pressure will be displaced by PC itself. And C is a C cube divided by C square minus A square plus minus 1 plus VU by UC by square minus V square by C, but here is PC itself and PC itself and C square minus A square itself. So total, this you have to add them together. Actually, we are subtracting from here this portion because this is creating compressive load and this is creating tensile load. So we are just subtracting them from each other, can make certain simplification to reach this particular position here, where P, A and C and U are all known to us. Next, for the steel bracket, we know the same equation we have to put the Poisson's ratio of steel, Poisson's ratio of steel, Young's modulus of steel, and the internal radius C remains as it is. It is the internal radius of steel jacket itself. PC is the stress created in the internal surface of the copper and tube. The same pressure is applied for steel as well as for copper. B is the outer pressure of the steel tube, outer radius of the steel tube, and C is following the inner radius. And here, same things are used here. This is the static, it is a steel tube, Poisson's ratio of steel tube, Young's modulus of steel tube, and the inner and outer radius of the steel tube itself. And this is the pressure P, which is initially created by this is the pressure PC itself. It is not P, but only PC. But here we have both of them. This is PC here it is P and here it is PC. There are two equations for them, but here we have only one equation because only one force is acting here, no external outer forces here. So the displacement of radial displacement of steel tube, this is the steel jacket, will be equal to, will equal these two portions, this one and this one together, and this is the rear portion and this is this portion here. So what we are having next, we are reducing to a certain extent like this. We have brought PC in this side and brought PC the right side, and after few simplification, we got the equation in terms of PC in terms of P. Now, here we can now use the numerical values itself. What is the numerical values? We know the internal radius of the copper tube is, external radius of the copper tube is given, internal radius of the copper tube is also given. And Young's Poisson's ratio is known, for copper tube is known, and outer radius of the Poisson's ratio known, and Young's modulus is also known. We can put all of them here. B is the outer radius of the steel tube, and C is the inner radius of the steel tube. The Young's modulus of copper, Poisson's ratio of copper, Young's modulus of steel, and P square minus S square, which is equal to, in terms of P, 2 into A is the innermost radius, and E into copper divided by C into A. So P is equal to 1500 kg per centimeter, you know. A is given as 10 centimeter, C is 20 centimeter, and B is 40 centimeter. V is known 0.3, V steel is known as 0.3, V copper is known as 0.34. If we put all of them together, all in the place, get the simplification, we'll get PC is equal to 4.33 kg per centimeter square is equal to 422.453 kPa. Now we got the value of PC. Now what will happen? This PC will act as an external pressure on the inner copper tube as an internal pressure of the steel jacket. So we are using them next to equation 11 and 12, which is also discussed. Sigma R inner surface, radial stress at the inner surface, where R is equal to A is equal to 1500 given minus 1500 because it is compressive in nature. Sigma theta is the circumferential stress at R is equal to A, is also given by this equation. So here we are calculating this and having 1357 kg per cm square compressive. And outer surface at sigma is equal to sigma R and R is equal to C, means the inner surface of the radius is given by is equal to 433 kg per centimeter square, which is equal to the internal radius here, this one, and this is given here. And sigma theta they are we putting the respective values of sigma and get 279 kg per centimeter for steel jacket. So at inner surface, sigma R at R is equal to C is equal to minus 433, and sigma theta at R is equal to C at is given as 433 into 400 by 1600 into 400 by 722 kg per centimeter square. And outer surface here R is equal to R minus B is 0, and theta R minus equal to B is equal to 433 into 400 divided by 289. So we have got the, as per our requirement, sigma R, sigma B, theta, radial stress at the outer surface of the steel, radial steel. Let us start again. God knows how many times it will stop. Now, let us go for the next item. The sphere with purely radial displacements. So far we have discussed the the cylinder which has m length and which has some longitudinal direction, longitudinal stress on the point itself, which mostly we have neglected. But sphere don't have any longitudinal stress.